Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 31st Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I will link to Project Euler and my repo in the description. Let's dive in. Problem 31 is coin sums. In the United Kingdom, the currency is made up of pound and pence. There are 8 coins in general circulation, 1 pence, 2 pence, 5, 10, 20, 50, and then 1 pound and 2 pound. It is possible to make 2 pounds in the following way. 1 1-pound coin, 1 50-pence coin, 2 20-pence, 1 5-pence, 1 2-pence, 3 1-pence. How many different ways can 2 pounds be made using any number of coins? So, I am going to go ahead and copy the problem statement over. This one's going to be interesting. Because first we're going to have to do a bunch of examination to see if we can find the pattern here. Let's go ahead. Okay, so there's a few very obvious combinations here, whereas there's one of the 2 pound, or like 2 of the 1 pound. And then you can get 1 of the 1 pound, 2 of the 50 pence, and just kind of so on and so forth. All the way down eventually to 201 pence. So I think the strategy for this is to start with the 2 pound coin and be like, that's 1. And then, kind of gradually replace. Or, let's think about this more mathematically. So the goal is you have 5 numbers, or 8 numbers, sorry. 2, 5, 10, 20, 50, 100, 200. And we really just want to find out how many ways can those numbers add up to 200. So rather than thinking of it in terms of actual physical coins, this is really, like most of these, this is a math problem. So we have to think of how to solve it with a math formula. And this problem does have one of those documents attached, so we'll be able to look up the suggested solution afterwards. Gonna try to solve it on our own first, of course, as always. Which we can't actually see the document until we have the correct answer, but, you know. So we have... let's see. So let's do the trivial cases, which is 200 ones, 100 twos, 45s, right? Because 4 times 5 is 20, so 200. 20 tens, 4 50s, 2 100s, and of course 1 200. So those are the trivial cases, and what I think that we could do to like brute force this would be to start at either end of the extremes and just sort of slowly replace coins. But I think that instead of brute forcing this, it would be smarter to find the formula. So let's go ahead and Google this, which is the smart way to see. Calculate number of ways to reach sum. Okay, so this isn't the same problem, but it is close. Okay. So here they have this example of they want to sum to 8, and they have 1 and 2 as the values. So the naive approach is what I was talking about, which is to generate all possible combinations and just count them. But that has the time complexity of OK to the n, which in our case the numbers are small enough that like that's not a big deal, right? But let's not do the naive approach. Let's jump straight to the efficient approach. Which, not reading that yet, obviously, but this has a time complexity of O and times K, which in our case is like 200 times 8, so only a few thousand. Like 1600 instead of, it would have been 8 to the 200th, which is a much big number. Okay, the above approach has overlapping subproblems and an optimal substructure. I don't actually know what that means, personally. We can go look into those articles, maybe. But I think that, like, this overlapping subproblems is like, oh, you're coming up the same combination more than once, maybe. Dynamic programming is needed to be performed based on the following observations. Considering DPI stores the total number of ways for representing I as the sum of integers lying in the range 1k. This transition of states can be defined as for I in the range 1 to k, and for every j in the range 1 to n, the value of dpj is equal to dpj plus dpj minus 1 for all j question mark I. So this is to initialize an array, which is a list in Python. I'm going to go ahead and look at the Python code. It's been a long time since I've used C++ regularly. To store all the recursive states, initialize dp0 as 1. Iterate over the range using a variable I and perform the following steps. Okay. This isn't quite making sense to me in words, so I'm just going to look at the code. Number of ways in K, initialize list is... They're doing it this way. I feel like that might not need to be done. And then they're doing this, which again, I'm not sure I understand the logic of why to do that. And then they're doing this iteration. Okay. So our in is basically 200. So, okay. Thinking this through. So, for 1, starting with 1, if column is greater than or equal to row, update the current dp column state. So for 1, 1, it does nothing. Come back to the second loop. It becomes 2. So then we update at index of 1 to be index of 1 plus, in this case, 0. So just 1. And then we get to 3, column is still greater than row. So then it would be column minus row. Okay, so column minus row wouldn't be 1, it would be -1. That's why they initialized the list like this. Okay. So, like, again, now that I'm actually looking at this properly, 1 and 1, 1 is not, or 1 is greater than or equal to 1. So, in index 1, we set it to 0 plus, in the first case, it's going to be 0. Or rather, it's going to be 1. Okay, I think I see how to make this work. We're gonna go ahead and copy this code over so that we can work with it. And then I'm going to try to explain it once I'm pretty confident that I understand it. Okay. So instead of N and K here, actually, I'm gonna make this not a method. No real reason to make it no longer a function. I just don't prefer it for what we're doing right here. And then obviously we need to print. And they're doing dp of n, which in our case would be like index of 200. Actually, let's go ahead and set a limit here. Or, no, we don't have to. We just set n to 200. We could rename this to limit, but let's keep it as n, just to make things a little less confusing, perhaps. Hopefully. And k can't just be 2, actually. K has to be... Let's see, is this the only place k is actually used? K has to be this array with the 1, 2... I'm just gonna go copy it from line 8 here. And let's see... They did not give us, like, an answer for a particular number, so we might change this to a different n where there's a more trivial case. Like, say, n of 10, because for n of 10, we can see that the combinations would be, like, 110, 2 5s, 1 5, 2 2, 1 1. Then we could have 1 5, 1 2, and 3 1s. Maybe we should try a more trivial case, actually, so just to see if we get the correct answer. So 1 5, 2 2, and 1 1, 1 2, and 3 1, or simply 5 1. So that's 1 2 3 4. So we should get an output of 4 if this algorithm works as expected. And that's really it. So for row in K, and I'm just going to delete these comments. Okay, so again, this should spit out 4. And it did. So if we give it 10, seems reasonable. We want to do all the way to 200. Okay, so if this formula works the way that it's supposed to, this is our correct answer. So let's go ahead and find out. I'm willing to bet that this is the formula that we are supposed to use. Yep. Okay, so that is the correct answer. Let's go ahead and go look at that little cheat sheet that they give you after you've completed it correctly. Okay, so it talks about starting with the largest coin. Therefore, the ways to make 2 pounds with any coins are 1 plus ways to make 2 pounds with smaller coins. Zero times... Okay, so it's saying if you don't use the 1 pound coin, then it's even smaller coins. Up to 2 pounds. Number of ways contained in the first group can be expressed like the original problem without the 2 pound and 1 pound coins. For the second group, we have the original problem with a target amount of just $1 and without the 2 pound and 1 pound coins. The third group counts as just one way, since the target amount, 2 pounds, is a multiple of the largest coin. In general, W of TC equals 1 if C equals 1 or T equals 0, and the sum of all of this if C greater than 1 and T greater than 0. Where T is the target amount, C is the value of the largest available coin, S of C is the value of the next coin smaller than C, and W of TC is the number of ways to make the target amount T with coins of value C and or smaller coins. Okay, so then they have a recursive function where coins 1 to 8 equals our values, and then the amount is 200. If ABC is less than or equal to 1, then return 1. Result equals 0, while target greater than or equal to 0. Do result plus res plus ways, and then it calls itself again. Okay, so I think this is potentially the recursive way to do what we just did, but I'm not 100% certain. Oh. It says this calculates the correct result in the blink of an eye. It's far from optimal. Okay, so this is similar to the first option here. Remember how we kind of skipped this one because why do the suboptimal way? So this is using recursion to calculate it, and it probably adds in this because K is just an iteration, or K is just a count instead of, like, it's 1, 2, etc. instead of these specific values. But then there's this part. So yeah. So the value of W2 to 10.2 is calculated 94,300 times. So that's what is meant by this overlapping subproblems. We can use memoization, which is just like a dictionary. They're saying make a dictionary with all the already calculated amounts. Or, well, they're doing a double array here, or a 2-deep array, or whatever you want to call it. But you could do this in Python very simply with a dictionary, and it would probably be easier to read and stuff. So then they're like, we can optimize this somewhat, remove those overlapping subproblems by using this dictionary type structure. And it says this version computes the ways to make 10 pounds in 4 milliseconds at the cost of using an array of 27 kilobytes approximately with 32-bit integers. With this particular set of twines, the array size might be reduced due to the fact that many elements are never used. Though we will focus on a more drastic optimization. And here's the part where I bet they're getting into what we actually kind of did. So let us analyze the dependencies between the different values of w, t to the c. And it has this chart with a bunch of arrows. The function wtc can be reformatted as follows. 1 if c or t, c equals 1 or t equals 0. W prime tsc. It is as straightforward as the previous version to the ways to make 2 pounds with $1 coins and or smaller coins, for instance, include ways to make 2 pound with coins smaller than 1 pound. This is the 0 times 1 pound case. Ways to make 1 pound with 1 pound coins and or smaller coins, cases 1 or 2. If we implemented this literally, we would get a very inefficient solution since it uses recursion instead of the loop of the initial program. It would be slower and it would use too much stack space. The maximum number of nested calls would be proportional to the target amount. Having said this, the interesting aspect is the graph of dependencies within different values of the function. So now it's showing these arrows drawn a different way. Note that some of the arrows depicted in the table, first column and first row, do not represent recursive calls of the function since it has been directly defined as 1 in these cases. The ones from the first row and the first column follow longer paths of additions until they reach their final destination. In exchange, every element is calculated by adding at most 2 other elements, thus we can pre-calculate the whole array in less time. Furthermore, every w prime tc element depends at most on a previous element of its column c and the element at the same row t in the previous column c minus 1. So yeah, this is sounding very familiar to that Geeks for Geeks article. Due to this interesting fact, we can use a simple 1D array, calculating a full column at a time while we overwrite the previous column. The next program is an adaptation of this solution provided by Wisman, post number 16 in the thread for probably 301 in the forum, so cool. Using 64-bit numbers, it can calculate, for instance, the ways to make 100 pounds in 3 milliseconds, setting amount equal to 10,000. So we have our coins array, which is what we did. We have our amount, which is what we did. We have our ways array, which is, again, that's our DP. And then our ways of 0 is set to 1. And then for I equals 1 to 8, do for j equals coins I to amount. And then we have this ways of j equals ways of j plus ways j minus coins. So obviously this is very, very familiar. It's a little bit different. They are doing this such that, like, we start with the j equal to effectively so first of all, they kind of flipped these two numbers around. And they've also done, instead of an if statement here, they've just made their inner for loop so that that if statement would always be true, which is pretty nifty. The second program solves some problems on demand, attacking the largest problem first and moving to smaller and smaller subproblems as required. It represents the top-down approach of dynamic programming. The third problem, instead, starts solving the smallest subproblem, and then it solves larger and larger subproblems. It represents the bottom-up approach of dynamic programming, and it is significantly faster for several reasons. As mentioned above, every element is calculated by adding at most 2 other elements. It requires less memory and accesses it in a cache-friendly way, and it uses loops instead of expensive function calls. So it turns out my let's not make this a whole function was kind of on the correct track. But also, that's trivial. We're in our code, it was call a function once versus call a function 0 times, so very trivial difference. First reason is quite important from the point of view of computational complexity. A memoized recursive implementation of W prime TFC, though maybe stack abusive, would also be faster than the memoized recursive implementation of WTC. Interestingly, when memoization is used, the maximum number of nested recursive calls depends strongly on the order in which the 2 recursive calls of W prime TC are issued. Huh. Okay. So, after all of that, effectively what they're saying is, if you do this way, which is, again, very, very similar to that solution we found on Geeks for Geeks, it calculates our answers by adding 2 numbers together. Now it has to add 2 numbers together, like in this case, let's see. Something like close to 1600 times. It's not going to be quite that because it has this tiny optimization here. But that's still far, far fewer times than like trying to find all the combinations and count them, or going the other direction. Okay, so let's see. I would say that one thing we learned is this is a whole new way of looking at the problem. Instead of trying to figure out this brute force naive approach, finding somebody already wrote out a formula. This is one of my most used ways of doing programming, is looking to see if the problem is already solved. Because if the problem is already solved, why spend a bunch of time and energy trying to think of a solution? Now, in this case, it's a little bit different because we are trying to learn. Not only are we trying to learn, but we are trying to solve these problems more or less on our own. But the difference I see is that we did not look up, okay, here's the exact problem, how do I solve Project Euler problem 31? We looked up a generalized version of that problem and adapted it to the specific problem. And I think that is a great compromise between wanting to learn and not wanting to reinvent the wheel necessarily. Because if I had tried to figure this all out on my own, I mean, I think that I could have come up with this part, and probably even the optimization of what they're calling memoization up here. But I would not have come up with this on my own personally. So, for me, being able to find, oh, here's something kind of similar, let me tweak it so that it gives us the correct answer, is a great way of finding the solution while still being able to internalize the lesson. So, I'm going to call it there for today, and I'll catch you in the next one.